applied math. And I have to apologize for the title of the colloquium on the website. So the actual title is How to See Things in the Most Efficient Way.
Thank you. I guess he's not here, but I'm going to wish happy birthday to Jack Milner today. Anyhow, yeah, so I'm in the applied math department, just around the corner, and I work in the area of computational geometry. A lot of the work I do is algorithmic and involves approximation algorithms. So I'm going to talk a little bit about both of those in the context of a geometric optimization problem, how to see something in the most efficient way, and I'll explain exactly what I mean by that. So the canonical problem you should have in your mind is what I call the Watchman root problem. It's a classic problem in computational geometry. I give you a polygonal domain, so it has an outer bounding cycle, what we call a simple polygon, but this isn't a simple domain because topologically it has genus 2, it has 2 holes. So the region is this region of genus 2. And my goal is to see it in the most efficient way, let's say by a traveling observer, a mobile robot that has a camera, is going to move around, and if it moves on this red closed loop, this maybe is a cycle of minimum length, or I look for a path of minimum length, such that every point of the polygon, every point of the space I'm trying to see, is seen by some point on here. And by see, I mean that you cannot see through walls. So the white segments are obstructions, just like the cinder block walls of this room. I cannot see through them. We also work on a version called the Superman problem, where you're able to see through walls.
You can't see from this point here, you can't see that point.
Well, okay. So from the tip of that red, I think you can just see it there. At least that's the interactive problem. Yeah. Zoom in on it. Okay, so the general problem is to find an optimal set, whatever that means. Maybe it's minimum measure, or minimum cardinality, or it has some combination of metrics. Find an optimal set X that sees all of a set Y. That means each point of Y is seen by some point of X. And that's the general class of problems, and we've barely scratched the surface on trying to solve it. So there's a lot left to do. And in the context of the Watchman root problem, we call these geometric covering tours. So I'm trying to find a tour that covers a geometric domain. So of course, I should say, what are geometric covering tours in a broader sense? So if you go to Google, you get the answer. So I typed in geometric covering tours just to see what I would get. And in Africa, there's a company called Geometric Tours, and you get this. This is exactly the page that Google thinks you need. Well, actually, that was before I gave this talk. Now that I've given this talk, I think this pops up. So this is what it used to be. So what do I mean by covering tours? So I have some set I want to cover. Say I have a discrete finite point set in the plane. And I want to cover it by visiting every point. So that would be what we call the traveling salesman problem. Find a shortest tour, find a closed cycle of minimum length that covers or touches every point of the input set. And that's a classic problem in optimization. It's known to be NP-hard. It was proven by my thesis advisor many years ago. And we now have very good approximation algorithms that let you get close to an optimal solution for this. But that's where you're visiting a set of points.
Does that require to be embedded like that one was?
Well, if you find the tour, it will be embedded. So, I mean, this is embedded as a polygonal cycle. So I'm measuring the length of that polygonal cycle, and I'm minimizing it. So I will... essentially, the output of a TSP algorithm, code, would be the permutation, the cyclic permutation of the points. And that implies an embedding. And it will necessarily be a simple cycle. If it self-crosses triangle inequality, we'll tell you can improve it. So it will have a simple embedding. In fact, that's one proof that any finite set of points in the plane has what we call a simple polygonalization, is that the TSP polygonalization works. So TSP we understand quite a bit. A variant of this we're still studying, called the TSP with neighborhoods. If I give you not points, but say I give you disks, these are unit disks. Maybe I want to go around and gather data from sensors that are in the plane, or covering precise points, or school bus routes where kids are able to walk up to a certain amount. Find the shortest tour that visits a set of disks. That's a problem we call the TSP with neighborhoods, and we've been studying that for a long time as well. This is circular neighborhoods. More generally, you might be trying to cover a set of polygons, and that's also TSP with neighborhoods. There's many different types of neighborhoods, and I've been working on a large class of such TSP with neighborhood problems in many different dimensions and spaces for quite some time. So our problem falls into that category. Here is my polygonal domain. It has a set of points. There's one point. You must see it. Therefore, you must visit this green region. You must visit that green region and that one and that one. These are the visibility polygons from these discrete points. But in fact, you have to visit the visibility polygons from every point. So it's a continuum of neighborhoods that must be visited. And that's what the Watchman route is doing. So it's finding a shortest covering tour, a TSP tour, that must visit every visibility polygon. Furthermore, it's subject to a constraint that it must stay within the polygonal domain. It cannot cross walls. So it must visit every visibility region, and it must stay within the confines of the domain of interest, in this case, the polygonal domain in the plane. So that's the Watchman root problem. It's a geometric covering tour on the set of all visibility polygons, all visibility regions for all points in the domain. Okay, and motivations come from all over the place. Practical motivations come from robotics. These are sort of crazy-looking paths. This is an early paper on exploration strategies for a mobile robot with a continuously rotating 3D scanner. So it has eyes in the back of its head and can see in all directions. And you want to, this is a floor plan, and it wants to go and inspect every room in the building kind of thing. What would be the most efficient tour? And I'm quite confident that none of those are the most efficient tours. But what they're trying to optimize is the length of a visibility coverage tour. And there's, in the practical problem, very often you don't have a map of the building. Today I'm going to assume that we have a map. We know the geometry of the domain we're looking for. There's also a very interesting problem, the online problem, where you're discovering it as you go. You're unfamiliar with the room or the building. You enter a building on campus that you've never been in before, and you must go around and sort of, maybe you're trying to draw a floor plan of the building. Then you're doing an online version of the Watchman root problem.
In that illustration, they aren't even tours by your definition. You have embedded circles always, right? Whereas these, they do start in the same room.
So I'm going to loosely go between embedded cycles and embedded paths. From the approximation point of view, it doesn't really matter. So I'm looking for small length curves that visibly cover a domain. But you're right. These are traces of a mobile robot that they ran in an actual experiment. And that's what they got. There's a long history. I'm not going to the computational geometry audience, I might go through all of this. But it started in 1986 with some work on Watchman root. It has, this is just a subset of the papers on it. I should say that results were published in the leading journals like Discrete and Computational Geometry. That's our leading journal in the field. Unfortunately, years later we discovered it had a fatal bug and it didn't work. Then it was open and then it was fixed and it was published, and that didn't work. And then it was open and it was fixed and that was published and that didn't work. So we now believe that we have solutions that do work. And these are the people that discovered problems and fixed problems, and they had problems and more things that were... It was sort of a comedy of errors. The bottom line is that we now have methods that all the groups involved agree are correct and have been refereed. Of course, the previous one...
never trust anything that's not in the premier journal in the area.
Well, maybe you should never trust anything that Tom Hales hasn't proven correct. That's another fact. Yeah, so I'm a co-author on one of them, in fact, on the latest one. And it's the most efficient one. So we distinguish between the anchored and the floating. Now this is for a simple polygon, no holes. So in a polygon with no holes, we can exactly optimize in polynomial time, order n cubed log n or n to the fourth log n. The difference between floating and anchored, anchored means you're looking for a shortest cycle that must go through a particular point, like the power charging station for your Roomba. Okay, so there's a depot where you must start and end, and that's given to you. Anchoring it makes it somewhat more efficient. If you're not sure where it goes through, even one point, then there's an extra factor of n in the algorithm. Now, these results of ours have been out there for almost 10 years, and no one's improved them yet. And conceivably, it could be solved in linear time.
This is the time to find the solution.
This is the time to find the solution. I'll give some hints how we do it, but that's not the main purpose of this talk. The main purpose of this talk is to deal with this harder problem. If you have not a simple polygon, but a polygon with islands and holes, how do you efficiently see all of it? And more generally in 3D, how do you see things there? There's tons of open problems. And in higher dimensional manifolds, we don't know how to solve any of these problems in any reasonable way. So there's lots of open problems. So approximation algorithms, where you give an algorithm that is provably within some factor of optimal, we do that a lot, especially for hard problems. But even for the simple polygon case, in simple polygons we can solve it exactly, but it turns out we can solve it, say, with a 2 approximation, so within a factor 2 of optimal in linear time, even for so-called floating Watchman roots. And various geometric observations allow you to get these things. I came up with also a square root of 2 approximation in linear time for the anchored problem. So you can do things faster approximately. What about polygons with holes?
I didn't quite understand what approximately meant here, but you're seeing most of the...
Okay, good question. So I'm still going to insist that you see everything, but I'm approximating the length of the optimal. So for me, most of the time today, but we look at this problem too, I'm going to constrain you to see everything. You could relax that constraint and say, what if you want to see 80% of it as short as possible? And so you actually have 2 objectives here, by criteria, the length of the tour and how much you see. And more generally, you might have a weighted domain, where some points are more important to see than others. In the art gallery setting, the Mona Lisa is more important in the Louvre than other paintings, and so you want to sort of see it better or make sure you see it, kind of thing.
A reasonable distance of it.
So,
The other end of the hallway.
Sorry?
I don't know if it counts if you see it at the other end of the hallway, which is...
As it makes its way out of the building, you mean?
No. It used to be that you could walk up and see the Mona Lisa.
Oh,
now
okay.
you can stand
That's okay. You have to stand at
1,000 tourists taking pictures of it.
Right. It's at least 10 meters away.
So if you designed an app for the Metropolitan Museum of Art where people enter the things they want to see most, and you return the...
So I actually believe there is an app like that works for some museums where you sort of hit what you want to see and then it does a TSP. I have a TSP app on my phone if anyone wants to see a TSP app in action. I can actually do optimal TSPs on 100 or more cities on my iPhone.
Begin by app.
What's that?
Stop and shop.
Stop and shop. That's right. So you walk into Stop Shop, you have your grocery list, and it plans the route through the maze of aisles for you.
Maybe begin by saying, what do you want, speed or accuracy?
So that's exactly the type of problem that we're solving. So in polygons with holes, really, everyone was up against a wall. We knew that it was hard. In some early work I did with a PhD student here, we had a log factor approximation. That's not very satisfying because it's not a constant factor, but turns out you're not going to be able to do better, as I discovered. This was in a rectilinear domain, axis parallel edges, and a special kind of visibility. The 2 points see one another if and only if they're rectangle. Bounding axis-aligned rectangle is a subset of the domain. It's not line-of-sight visibility. It's insisting on something much stronger. So it's sort of a fake problem. That's the only one that we knew how to do. Here, in this work that has just been published within the last year, we actually showed that for arbitrary polygons with holes, we get a factor that's log squared. Okay, I started this hoping I was going to prove a constant factor, like a 2 approximation. But while I was working on this and I kept running into this wall, I actually proved that you can't do better than a log factor approximation. That's the best possible unless p equals np, which we don't believe.
So omega means a lower bound?
Omega means lower bound. So the approximation factor that you can achieve in polynomial time is at least a constant times log n, and it's at most some other constant times log squared n. And so I hope, I'm still working on it, but the next paper I hope to write on this will make this tight. If I can make this order log n, then we call it tight and we call it theta log n approximation. That's where I believe we're headed. But this first result has a gap. Furthermore, the Watchman root problem in higher dimensions, Safra and Schwartz had proven 10 years ago that unless p equals np, you cannot approximate the 3D problem. And I'm going to conclude today actually by talking a little bit about 3D. That's where a lot of my interest is. 3D in higher dimensions, we'd love to get some insight.
Constant factor, what's the full statement?
Well, this is saying that there does not exist a constant c, such that in polynomial time, you can have a guaranteed approximation in polynomial time unless p equals np. And what I show is that it's not just that there's no constant factor, you must have at least a log factor. And that holds even for a very special kind of three-dimensional scene. Not an arbitrary 3D scene, but a terrain, so sort of what you might call 2.5-dimensional scene. Even that requires a log factor, as it turns out. So the problem has many variations. The Watchman root problem depends on the type of domain. Without holes or with holes in 2D. Without holes, it's polynomially solvable exactly. With holes, that's what we're mostly talking about today. You can also work in networks, one-dimensional networks, like roads and so on. I'll say something about that. I'm very interested in problems on terrains, where you have vehicles moving on surfaces. So we've had interest from the defense industry on that. And more generally in 3D and higher dimensions, I'm interested in all of these problems. There's anchored versus floating, of whether you assume that you know a point that it goes through or not. For approximation purposes, that's not really going to matter. Variations on visibility. I'm assuming, unless I say otherwise, I assume that it's line of sight visibility, and you can see as far as infinity. But you can also put bounded view distance to make it more realistic. And you can talk about robust visibility and limited aperture and so on, other variations on visibility. So there's lots of those.
Anchor means you give yourself one point on the optimal solution, or you just assume it goes through one point. You did two definitions of anchor.
So when I say anchor point, I assume that that's given to you, that there's one point that you must pass through.
Not on the optimal solution, or it is on that? You don't know.
I don't know. I'm going to force you to pass through it.
Okay.
It may or may not be on the optimal solution without that constraint. So it may be a binding constraint, it may not be.
The difference between based on the copy and free on the top.
How many? So most of the time I'm going to talk about one traveling agent, but the frontier of this problem, already when I get to 2 agents in a simple polygon, I already don't know how to proceed. That's an open problem. So how many Watchmen? Most of the time we're going to talk about one. And when you have multiple Watchmen, you could talk about minimizing the longest travel so that you're trying to balance their workload, so to speak. Or you could try to minimize the total travel, sum them up versus min the max. What's the objective function? By default, it's going to be the Euclidean length of the tour or path or whatever I'm building. But we've also looked at things where turns cost you something. So link length means how many turns in a polygonal chain. Also, in practical applications, you care about scan cost because you pause, you take the image, a high-resolution image, then you move, then you pause, you take another high-resolution image, etc. We've worked on that problem as well. And then, like I said at the beginning, there's both offline and online. Offline is what I focus on. That's where I give you the geometry of the domain that you're to cover. You're not having to discover it online as you go. Yeah.
So in the problems you've been talking about, is it clear that the optimal path will be a polygonal path with a linear number of vertices, or is even that not clear?
That's a great question. I hold that for about 3 slides. I'm going to pose an open problem related to exactly that question. Yeah.
In the online case, you could be discovering a unknown region.
Right.
Can the walls change?
Of course, it makes it even harder. Of course, that's what happens in truth. If you're trying to make, and so Google and other companies are trying to make accurate maps of many cities, and things keep moving, right? I mean, they not only move like cars moving and pedestrians are in your way and so on, but buildings change, and walls move, and bridges are torn down, and things like that. So, yeah, that makes the problem even harder. We barely have a handle on the simplest version of online exploration, let alone in a dynamic set. So lots of interesting problems that we don't know how to do. So 2 key things. Weighted region problem is a covering tour, and because I'm going to concentrate right now on a single tour, it has to be a connected set. So I want a connected set that visibly covers all the points of my space. Think of it as a polygonal domain for now. There's related problems in graphs. In graphs, we've looked at so-called vertex cover, where in a graph you want to pick a set of vertices that touch every edge. That's a classic optimization problem. And there's an optimization problem where I not only want a set of vertices that cover, but I want them to induce a connected subgraph. And it's called connected vertex cover, and that was worked on by S.D. Arkin here and her co-authors, and it's been improved recently. She got an approximation, and that's been improved. There's also something called connected dominating set. The dominating set is a set of nodes such that every node is adjacent to one of the ones in your set. So essentially it sees it. If you think of looking down an edge, if I stand at one node, I can peer down the edge and see the node at the end of the hall. If I insist on it being a connected dominating set, that's essentially like a graph version of this geometric covering tour. There's also related problems called group Steiner tree or group TSP, also known as one of a set TSP in graphs, where instead of having to visit a set of cities, you have to visit a red city, and a blue city, and a green city, etc. One of each color, one of each class. These are groups. So there's been a lot of related work, and these are all related to what I'm talking about. In the geometric setting, I gave a math club talk here not that long ago, I don't remember when. We talked about the classic art gallery problem. And there you're doing an optimal visibility coverage, but your metric is not length of a tour. These are static guards, and your metric is the cardinality of the set. How many guards are there? You want to minimize the number of stationary guards to see a polygon. So a classic example, I give you a simple polygon. There's a potential guard. He sees that region, but he doesn't see the whole polygon. If I take these 5 points, they form a visibility coverage of that polygon. And the algorithmic problem is compute such a minimum cardinality set. Compute G of P. For an input polygon P, determine this function. Now, it turns out that it's NP hard. It's one of these intractable problems that won't have a polynomial-time solution, we believe, even in simple polygons. So we tried to do approximation. This is one where we don't even know how to approximate it. But the combinatorial problem that was studied in mathematics in the early 70s that Kkt showed, it was a problem posed by Victor Klee at the beginning of the 1970s. And by an induction argument, he proved that any n-gon can always be guarded. N over 3 floor guards always suffice and sometimes are necessary to visibly cover an n-gon. So there have been lots of combinatorial questions of this flavor. This was the first one that arose from Victor Klee's original question. So now, of course, in our setting, one guard is enough if you let him be mobile. And then you're trying to minimize his motion. But all of these problems have had a rebirth in computer science and algorithms because they have a lot of applications to sensor networks, security, coverage, etc. Google is trying to solve these problems now, and that's caused a resurgence. So mathematicians who used to work in the closet on these problems now come out of the woodwork and are publishing papers all over the place saying, I work on sensor networks because of this. Yeah.
Are the worst three cases typical or very special?
Now, it's very special. It's something we call the fatal coma. I mean, there are other examples as well, but I don't know a characterization of what all of them look like, but this is a typical one. For every 3 vertices, I can add another tooth, and you can easily argue that to see each of these, in each of these spikes, you need another guard. So that's the lower bound example. There's a lot of art gallery theorems. There's a book called Art Gallery Theorems and Their Applications from nearly 30 years ago, and many of the open problems are still open.
Yeah, anything like that before you keep that?
Sure, people work on that all the time, but they don't have tight bounds there. I don't remember the exact upper and lower bounds, but people keep trying to tighten these bounds for polyhedra, for 2.5-dimensional space, for other kinds of spaces, and so on. I had a student a few years ago who graduated who had looked into several other combinatorial art gallery theorems in higher dimensions. And I just don't remember the bounds. The TSP with neighborhoods, I already mentioned, is related. Now, because we must stay inside the domain we're traveling in, there are obstacles. This is sort of a free-floating tour. So I work on this problem as well. I give you a set of regions, say in the plane or in 3-space, but here there are no barriers to your travel. In our case, there are barriers to travel as well. If you also have a bounded radius that you can see, then a related problem is the so-called lawn mowing problem. The center of your lawnmower, it's the center of a circular disc, the cutting radius, and you're trying to sort of mow or mill a pocket in the most efficient way. We worked for some years with some machining companies, Bridgeport Machines, that develops the software to move tools, and you want efficient tool paths that will mill out a pocket. And every time I mow my own lawn, I start a timer and time myself, and I'm trying to optimize
What?
cutting.
You don't have a robot?
I don't yet. I'm really tempted to do. For years, long before they had robotic lawnmowers, I was thinking of getting in the business of robotic lawnmowers and vacuum cleaners. So actually, when I was working from a practical point of view as a summer student in a robotics lab, I was with the guy who developed iRobot, founded iRobot, and started Roomba. So we were in exactly the same mobile robotics lab together. So we call this the D-sweeper problem. You're trying to move on a tour that visits a disk centered at every blade of grass. Right? So it's a TSP with neighborhoods, also with constraints, perhaps. That assumes that the white space maybe are your rose gardens and you don't want to mow them. We make the distinction between milling and mowing, in which you're allowed to venture outside of the gray region or not. And it really depends. Anyhow, back to our problem of the Watchman root problem. Let's try to understand the structure of an optimal solution or a nearly optimal solution. What needs to be covered? Remember, we have to visit the visibility polygon of every point in our domain. So that's what needs to be covered. Is it enough just to see all the vertices of the polygon? If I come up with a tour that sees all the vertices, will it necessarily see all of the polygon? Well, if you take my undergraduate computational geometry class, this will be a homework exercise. Yes, you could prove that seeing all the vertices is enough. So if you have a connected set, the blue set, it doesn't have to be a cycle, but a connected set that sees all the vertices must see all points of the polygon. Then part B of that homework exercise says what happens if you have a polygon with holes. And here I have a polygon with 3 holes, purple things. And notice that this blue connected set sees all vertices. But notice it does not see that red dot in the middle. In fact, it sees all of the boundary of the domain, and yet it fails to see some of the interior. Okay. So we need to insist on seeing more than just the vertices. Now, from an algorithmic point of view, this complicates our lives, because the vertices, that's a discrete set. There's only n of them. But now we actually have to somehow deal with this continuum, that we must visit the visibility polygons of every point. So it's not enough even to visit the entire boundary of P, or see the entire boundary of P. So in the simple polygon, without holes, the algorithms are based on this structure that, in order to see this point in that corner, you have to visit this green region. And we formalize that by talking about a cut. If you take this edge and extend it, and you look at this directed line segment, the region to its left is a region you must visit. And that's true here as well. Since you must see that tip, you must visit what's left of this directed chord. But since the region that's to the left of that is a subset of the region to the left of that directed chord, it's dominated. So you can get rid of this. It's enough to say you must visit this region, because assuming, say, you are somewhere ever on the other side of this, then you must visit that, and you will for free visit that. So you can come up with a set of what's called essential cuts. This is an essential cut. But here, there's a bunch of essential cuts, and you must visit each of them. And they form what's called a corner. There's a bunch of them that all intersect each other, and they don't dominate each other. Essential means undominated in this partial order. But you have to, your visiting tour must visit each one of these, and you might cross some of them. This could be a very complicated structure, these corners. And that's exactly where the original paper got into trouble, was with corners, and their proof broke down, but that was only discovered more than a decade later. And it turns out that you must visit the essential cuts, and you must visit them in the order induced by the boundary of the simple polygon. So by understanding the structure for Watchman root and simple polygons, it gives us a polynomial-time solution with a lot of extra work. You can find all these essential cuts efficiently, organize them. There's many different things that you can do there. If you're in a polygon with holes, it's trickier. There's weird things happen, like this red thing is supposed to be, imagine it's an optimal tour. These little spirals are tiny little spirals that have a point, have points in the middle that you have to see. Therefore, essentially, by making these spirals arbitrarily small, I can force my tour to go visit particular points, or the neighborhood at some point. That's what these little spirals do. But now I have these bigger obstacles, and I have to see all points. And so somehow I'm going over here and I'm bouncing off of this construction line. This green thing is a construction line. This is a construction line. And they're picked just so that if you look at this visibility graph edge defined by this tip and that, because you're passing by here, so you sort of have this tour, you pass by there, you see this, but in order to see that point P, you need to see a little, which is just missed by this, it's just above. You have to go visit A and B. And A and B are these, it's always the case that if you're going to visit a line segment, then by simple calculus or Snell's law of reflection, if you visit it and then leave it, you're going to do it angle in equals angle out. Right? That's the local optimality that Calc 1 will give you. And in the simple polygon case, we know in advance all of those essential cuts because they come from extending edges. There's a discrete, finite number of them given by the input. What this is illustrating is the difficulty in a polygonal domain is that there are construction lines that are vital to the definite or to the constraints on optimal that don't come from any polynomial-sized set of a priori segments that we know how to define. I know of no polynomial-sized set of essential cuts that work in the polygonal domain case. And this is what has confounded people that have worked on this for at least a couple of decades. So What other people have done, Adrian Dumitrescu and Csaba Tóth, have given some bounds. They said, oh, well, here's an upper bound on how far your Watchman route must travel. If you take the perimeter of the domain, that includes the boundary of all the holes, the total boundary length, plus square root h. H is the number of holes, it's the genus. Square root of the genus times the diameter of the region. That's an upper bound. Constant times that is an upper bound. And they prove that it's tight for certain classes of polygons. But that doesn't mean that this gives you anything close to optimal for a particular polygon.
That's curvy.
Perimeter. It's the length of the boundary, including the holes. Okay, so in a polygon with holes, it is NP hard. And just to flash a hardness proof at you, I'll do this. So it's known that if I give you points on an integer grid, finding a shortest tour on that grid, it's called a Hamilton tour of those points, that's a hard problem. I mean, deciding if there's a tour of length less than a certain amount. So you could turn this environment into a polygon with holes. So the outer boundary is the square, and it's got lots of square holes. And they're putting little tiny T-shaped things. This guy, it is representing each of the points. And because it looks like that, in order to see it, you have to sort of enter it and then leave it. So it's forcing you to go in this Manhattan map with these little T's sitting around. You have to go visit those points. It's forcing you to solve TSP, and TSP is a known hard problem. Therefore, visibility, minimum length visibility tour, is hard from TSP. It's as hard as TSP, if not harder. So I've already mentioned that the Watchman route in simple polygons, we know how to do it efficiently. I'm going to flip through these. This is the most efficient method. It's based on so-called the Turing polygons problem, where I give you a starting point, I give you a sequence of polygons, I'm giving you them in order. Find a shortest tour that goes from S to T that visits the polygons in the given order. That is, the first time you visit Pi occurs before the first time you visit Pi plus 1. And that's the more general problem that we set out to solve and do solve. And that allows us to solve this Watchman route in a simple polygon in polynomial time. It turns out, though, that this problem, which is more general, is hard if the regions are non-convex, as they are here. There's a very... we don't know... If they happen to be non-convex but disjoint, we actually don't know if it might be possible. We prove that it's hard if they're non-convex and possibly overlapping. There's an interesting topological version of this, though. Suppose I want a shortest path that goes from S to T and visits a sequence of points. So I'm giving you the order of the points. I want the shortest such path. Well, that's trivial. Just visit them in order using straight line segments to join them. But that might self-intersect. What if I want the shortest simple tour? So a simple tour or simple path is an integral. It's a simple path, or a simple cycle. So you can go from 1 to 2 to 3, but you're not allowed to go directly from 3 to 4 because that would self-intersect. You will have to go around to 4 and then around to 5 and to 6. I'm giving you the order. TSP on points is hard, but we think of it as being hard because there's n factorial different orders to visit the points. Here I'm giving you the order, but I'm going to insist on simplicity. In the TSP problem, I don't give you the order, but you know that the optimal order is such that there's no crossings, because triangle inequality implies that. Here, I'm going to insist that you visit them in the order I give them to you, but you must remain simple. And I want the shortest, or I want the lim sup, right? Because, I mean, in the limit, this is getting closer and closer. It's like these are nails, and you're just going around the end of that. So it approaches it only in the limit, but there's a there's a limiting. I want to know the lim sup of the tour lengths. Special cases. There's
So in that problem, do you know anything like maybe an exponential lower bound or something? Imagine that you'd be forcing yourself to spiral around lots and lots of simplicity. Those be some examples where you.
So we know that you never need more than root n times the length of the TSP.
Oh, okay.
That is actually an observation that Peter Shore pointed out to us, and Bob Conley. So Bob Conley and Peter Shore had talked about this. So it's related to, I mean, he didn't talk about this, but he talked about a problem of Bob Conley's on wire routing that I think I've mentioned to you before. And the same observation that Peter Shore made about that applies here. So we know how to get within root n times TSP. We don't know anything better. We don't know if that problem is hard, and we don't know how to approximate it better than a root n factor.
But what if I have half the points in a small cluster here, half the points in a small cluster here, unit distance apart, and I force you to go back and forth every time, then the distance is n, but I could have gotten away with 1 if I just visited them all here, and then went over and then visited them all here.
Let's see, so
So what's the question though?
The question is,
that looks like
that's
n
n longer than the
times
optimal, and
n times TSP. Yeah, so I have to change what I just said. So maybe
You're not allowed to change the order, right?
I can't specify the order.
You specify it.
he's specifying the order is going to go back and forth.
Back and forth between two little clusters.
Right.
Optimal would be to visit all of them here at the epsilon length, and distance 1 to the other cluster at epsilon length there.
Well,
Maybe it's on an integer.
no, but that's up. That's violating. So so you have a cluster here and a cluster here.
But he wants it embedded.
So 1, 2, 3, 4. So what's opt? So opt has to go back and forth. And,
Okay, I didn't understand what optimal was. Okay.
Yeah.
All right.
So we can get within root n times opt. And in that
So this
example,
is
it's
the optimal, not the optimal for visiting the set points. Okay.
right. That's right. So there's some other problems related to this. I'm going to skip these. They have clever names to them. Zookeeper problem. You want to visit the convex cages. Yeah.
So in the Polygon with holes problem, suppose you ask for an algorithm that's polynomial in the number of vertices, but maybe exponential in the genus, let's say. Do people know anything about
Great
that?
question. This is what we often call fixed parameter tractable algorithms, where the parameter would be the genus. So we believe that in the case of Watchman root in a polygon with holes, it is fixed parameter tractable. It may even appear in the thesis of one of my recent students. So, because there you can, for instance, you could imagine that you try all exponential in genus ways of interconnecting the holes, turn it into a simple polygon. But the problem is that you're artificially creating some walls that go into that simple polygon, and you can see through them. Whereas if you just apply the simple polygon solution after you've merged holes to make it simple, it solves a different problem. So I'd have to check on that. But I believe it's known. I believe we know that it can be fixed parameter tractable in the number of holes. But I'm not certain of that. At least you can get approximately. There's Safari problem, there's Zookeeper problem, there's the Watchman root problem. All of these fall within this category of visit a set of regions in a prescribed order. In the Watchman root problem, in a simple polygon, it becomes one of these things and visit the essential cuts in an appropriate order. And that's how we solve it. But it's a lot more complicated than that. And I'm not going to speak about that solution. I want to give a hint about the case with holes in my remaining 10 or 15 minutes. There's special cases where we can solve optimally in linear time, like if it's a rectilinear polygon. This is actually a figure from the very first Watchman root paper, hand-drawn in those days. And they drew some essential cuts and they shaded the regions that you must visit. And then they unroll it into, these are from their paper, you have to visit these, and you know you visit A, B, C, D, E in this order. And you take a copy of this, you duplicate, you fold it over, and you make another copy. So across B, you fold it, and then you fold it across C, etc. So you're making a covering space here by replicating copies of the triangulated polygon. And then you converted it to a problem of finding a shortest path from segment A to a copy of segment A. And it actually turns out that can be done in polynomial time. The special fact you're using about rectilinearity here is that the essential cuts don't form these nasty corners. Because they have to be horizontal or vertical, the worst complexity you get is just two of them meeting like that. So this unfolding, unrolling the polygon allows you to solve it particularly efficiently. Other special cases, if I give you an arrangement of lines, so here's a union of lines, infinite lines, in the plane, and you must travel on those lines, and your goal is to see every point of that union of lines. And by see it, if you're on a line, you can see every point on that line. That's the rule. So, and we had a paper, Pavel Zelinsky, Adrian Petrescu, and myself had a paper a year and a half ago where we gave an exact algorithm to solve this problem. He's actually going to be visiting at the end of March for about 10 days. So we're going to work on some more Watchman problems. So it turns out you can find, so you must travel on these roads, and you're trying to look up and down every road. And by proving structure results of what it looks like, and then giving a recursive optimization algorithm, we solve this exactly. Other special cases, maybe your roads aren't infinitely long, they form a network like this. This is what we call planar straight line graphs, or arrangements, segments. And that problem is NP hard. It's sometimes known as Frank's problem to try to approximate it. In our paper, we gave a log cubed approximation for that. In this talk, my techniques improve that to a log squared approximation. If the segments are axis parallel, then in fact you can get a constant vector approximation. These are special cases of the Watchman root in a polygon with holes, because this white region is a polygon, a polygonal domain with holes. Each of these bounded faces is a hole. So this is a genus 4 set. Right? And as I said, I proved a lower bound, omega log n, on the best factor you can do to approximate the Watchman root in a polygon with holes. And I'm not going to go through the proof, but I'll give you a hint of what's involved. You take a problem that already has a log n lower bound, and you reduce it to your new problem. And the problem I'm using for the reduction is something called set cover. You have a finite set U of elements, and you have a collection of subsets of U. And in the set cover problem, your goal is to pick a minimum cardinality subset of sets whose union covers U. And that's a notoriously hard problem. In fact, it's not only NP hard, it's NP hard to get better than a log factor approximation due to a result of Yanakakis et al. So I proved that if you could get a Watchman root solution whose length was better than if a constant existed, so if you could do it within better than constant times log n factor, then P would equal NP, because you could solve set cover better than what's known, and someone else proved that that would imply P equals NP. So unless P does not equal NP, you can't do better than the log factor, and I'm just going to flash the slides and not go through it. That's what we call a negative result. You can't do better than a log factor. And that was disappointing to me, because for many years I was searching for a constant factor approximation. Thankfully, I found the lower bound, so I didn't spend more decades lumping my head against that problem. So instead, I turned my attention to trying to get a log factor, and I didn't quite manage yet, but I can get a log squared factor. So I claim that you can get within log squared times optimal for a Watchman root in a 2D domain. And there's two things I do. I have to deal with so-called localization. We have no idea even approximately where this tour needs to be. And the other is discretization. This comes from that difficulty of I don't have a discrete set of essential cuts that I have to go visit. There's this continuum I have to deal with. And to deal with localization, I consider a polynomial number of so-called minimal outer illuminating squares that the optimal solution has to pass either near or through. I'll have a picture to illustrate this in a moment. So the main idea is I'm going to solve two related problems that together give an approximation to the overall problem. One is the so-called outer Watchman root problem. Find a short tour within my domain that sees all of the points of P that are outside of the tour. I don't care about what's inside. Just find the shortest tour that sees everything that's outside of it. It doesn't have to go around all the holes. Some of the holes could be outside, some inside. Just among all possible simple closed curves in the domain, look only at those that see all the points that are outside and find the shortest one. So that problem I solve in some sense exactly. I have to discretize it. I have to sort of snap it to a grid. But I solve it exactly in the discrete setting. I solve it with a so-called p-task within 1 plus epsilon times optimal in general. Now, once I find one of those, I'm going to use that cycle as a base and solve this other problem. The inner Watchman root problem says, given a curve gamma, simple closure curve gamma within the domain, augment it with a minimum measure network that allows you to see all of the points that are inside of it. And for that problem, I don't know how to solve it exactly at all. In fact, it's closely related to the set cover problem. But I can use results known from set cover. Namely, set cover has a log factor approximation and a structural result on geodesic triangulations that gives you a log squared factor. And then I argue how you can put the two solutions together and get an overall approximation. So now, back to Chris's question. What do we know about the structure of opt in a polygonal hole? So if I give you a polygonal domain that has n vertices, total of n vertices on the holes and the outer boundaries, I certainly believe that the optimal solution, whatever it is, forget about computation, is a polygon with at most order n vertices. I don't think it needs more terms. But there's this continuum of segments I need to visit, and I don't know how to bound it better than n squared at the moment. This is a lovely open question. So by some simple arguments that I don't have time to go through, I can prove that the optimal is a polygon with at most order n squared vertices. I strongly believe it's order n vertices. And I think there should be an elementary proof, but I've been stuck on this for a while. So that's a great question on the structure of opt. Now I said for solving this outer vision problem, I was actually finding a minimal outer illuminating square. What do I mean by that? So it's going to be a square. It doesn't have to lie within the domain. So see, parts of this square lie outside. But if you were to put lights on this boundary, at least on the portion of the boundary within the domain, it would see everything outside of it. So there can be holes outside of it, but every point outside of this square intersect with the domain is seen by the boundary of that square. And I claim that I can find such things in polynomial time because if you take any such square, you can shrink it. And there's an argument whereby you shrink it continuously. A square has only so many degrees of freedom. And so as you shrink it, maintaining the outer vision property, it will get stuck. It will be pinned. And it will be pinned algebraically by certain features of the space. And there are only a polynomial number of such features. That's how the argument goes. And so you only need to check a polynomial number of such roots of an algebraic system, actually. So once we have conjecture, so we consider all of these minimal ones, and this is minimal, not necessarily minimum. We now go looking for, so if B is somehow minimal, I take it in large B that's at most n times the size, say the diameter of B. You never need to go bigger than that. And that uses a simple proof having to do with triangulation or vertical decomposition of the domain. Again, I see my time running out, so I'm just going to hit the highlights. I get it. So I have an approximation that I can argue that I'm rough. It suffices, since I'm going to enumerate over all of these different discrete choices of minimal boxes, and that if that minimal box is the right one, associated with opt. And associated with opt, there will always be a minimal box. Because if you surround opt by its box, it is outer illuminating. Because opt is outer illuminating and inner illuminating, but it's outer illuminating. So if you find a minimal box around opt, and I'm finding things that are possibly even smaller than that, and then I argue that it's between that and a dilation by a factor n, then I have an approximation. I have some rough idea of how big this optimal tour is, or roughly where it is. Because this space could be very complicated and I don't know where. So then I put a grid of an appropriate size. The appropriate size has an n squared in the denominator. It's the size of b over n squared. And then I can sort of snap, I can round my solution to this. So this gives me a polynomial number of discrete points. So the outer Watchman root problem is find a shortest curve gamma that sees all points that are outside of it, that are in the domain. That can be solved using, again, structural results. It's so-called geodesically convex. That means that geodesic paths, shortest paths within the domain, it's closed under geodesic paths. So that allows me to search for geodesically convex outer illuminating cycles, and I'm doing it within this discretized domain, so I can set it up and solve what's using so-called dynamic programming. So at this point, I'm just going to ask you to believe that. There's a recursive optimization that allows me to do that. So the outer Watchman root problem, in particular discretized to the grid, can be solved exactly in polynomial time, and approximately without the grid, the non-discrete version. The inner Watchman root problem, now that I give you gamma, and now you need to augment it, because this gamma doesn't see inside all of those caves. So you have to add some extra length, all the magenta length. And I want to minimize the length of that network to see everything. How can I do that? That's where I end up with a log squared approximation based on set cover. This is based on the concept of geodesic triangles and a geodesic hierarchical triangulation. We say that a triangle is inner illuminating if it sees everything within the polygon. But I'm talking about a geodesic triangle. So these are vertices A, B, and C, and I join them by shortest paths. The region bounded by that, all points within that, is called a geodesic triangle. And I look at geodesic inner illuminating triangles. And what I argue is that you can take gamma and geodesically triangulate it and get a covering. And I'm going to look for an optimal cover using weighted set cover, using a known algorithm called the greedy algorithm for set cover. I will perform the coverage. But I have to relate. I'm going to do an optimal full triangulation of, I'm going to do an optimal cover by geodesic triangles that might overlap. What I argue about opt is that whatever opt is, let me get to a picture. Here's gamma. Here's an optimal augmentation. Trace it with this white boundary. That's a simple closed curve. That simple closed curve has, there's gamma, has a geodesic triangulation. Here I'm going to go every other vertex, and then I'm going to go every other vertex, etc. We call this a hierarchical geodesic triangulation. And it has only a logarithmic number of steps, because at each step I'm going every other vertex and joining them by a geodesic path. Remember, this is inside a geodesically convex polygon. So, whatever the length of white is, the length of green is no longer than it, by property of geodesics and triangle inequality. The length of magenta is no longer than that, etc. Each layer in this hierarchy is at most the length of white. Because I'm doing every other, it's a logarithmic number of layers, log of n, where n is the number of vertices in white. So I've taken opt and I've made it into a network of length log n times opt that is a union of geodesic triangles that see everything. They're all interilluminated. Then, if I use my algorithm to find an optimal set cover in this setting, it will, and that algorithm has a log factor approximation. That's what's known. I'll be within a log factor of the optimal. Opt could be converted to a cover by geodesic interilluminating triangles. I found within a log factor the best such set. The two log factors get multiplied, and I have a log squared approximation. So I conjecture that I can actually get a log approximation using a totally different set of tools. But that gets more complicated, and that's a subject for another talk. So the overall algorithm is I enumerate each minimal outer illuminating square. For each of these, I establish a grid proportional to its size. I solve this discrete outer Watchman root using a recursion, a dynamic program. And then for that cycle, I solve the set cover, weighted set cover using a greedy algorithm to get the inner illumination, and I end up with a log squared approximation. And since I'm out of time, I'll postpone. There's a number of interesting questions in 3D that I wanted to possibly get to. The toy problem is this. If you have a 3D ball, that's an obstacle, and you're in 3 space. Find a shortest path or shortest cycle that lets you survey the planet Earth. So you're a satellite in outer space. Move a satellite on the shortest route, path, or cycle, so that it sees every point on the surface of the Earth. That's your homework problem. I can tell you what solutions we have and what their lengths are, but you might come up with your own conjecture. We don't have type bounds or proofs of even how to see the outside of a single ball, let alone 2 balls or a complicated domain. So right now I'm working on 3-dimensional and higher dimensional manifolds, trying to do these visibility coverage things, but time is away from me, so I'll end it here and take questions. Thank you.
Any question or yes?
What is sort of the largest problem in this area? This can be done by today's computer.
So are you asking what's the largest problem or most significant problem?
It can be to the traveling sales problem for all towns in the United States.
How many cities?
Oh, what's the large? My colleague Bill Cook, who's sort of the guru of solving TSP. In fact, there was a book that came out last year called In Pursuit of the Traveling Salesman problem. It's a great read. He's the one who developed the iPhone app. It's for free. I send you the link for it. The iPhone app, we can easily solve random instances of several hundreds of cities on your iPhone, which was unheard of a few decades ago. I mean, supercomputers weren't solving it. Now, I think he has an award posted, sort of like Erdos did, for solving 100,000 city to provable optimality. I think we're up to like 40 or 50,000 cities, but 100,000 has a reward associated with it. Now, that's not to say there aren't instances of TSP with millions of points that we can't, that we can't solve to optimality. I mean, the points are in convex position. I can solve it to optimality in less than a second. But in general, it's a question of what kind of instances, what structure is lurking there So I think his prize maybe he provides the data for this prize.
But I have to provide a proof that I think is optimal.
That's right.
There's no way of checking that my answer is the best one.
That's right. So his methods, which are based on primal dual methods in integer programming, actually sort of comes up with a certificate proving that this is optimal. So his are provably optimal when his code solves it. If you download a free app called Concord, like the airplane does. Now, Concord TSP. Concord is the program that will solve TSP, and you can play with TSP instances. You can also do it on the web. Concord has a website, and you can put in your own data, or you can have it generate random data, or you can click data, whatever you want, and it'll solve TSP instances. So on point sets in the plane, we do pretty well. Point sets in other metric spaces, discrete metric spaces, there's several notoriously hard TSP instances. So there's a site devoted to the TSP Live, where you can go and get these hard instances. So it's all a matter of how hard the instance is. Yeah.
You worked pretty hard to get, you worked very hard obviously, to get a log squared approximation for a particular form of the problem.
Right.
Now in higher dimensions, I'm assuming that your hopes for constant and log squared fade away, and you have to settle for worse and worse approximations.
Yeah, if I were to make a conjecture, I think this, so in a polyhedral, so in a cell complex of complexity n in dimension d, I would conjecture that you can get a log to the d approximation, factor approximation. I think the dimension's going to enter in the exponent.
Yeah, that was part of the question, and the other one is at some point you're going to be better off opting for a random walk, like a Monte Carlo.
Sure. So
Markov.
Here I'm today I was provable approximations.
Are there problems where you are actually competing with the Markov chains with the deterministic approximation?
I don't know. Nobody's done those kinds of experiments to compare. I'm not claiming that the theorems I'm proving today are practical or competitive with heuristics that Bill Cook or others would have for my problem. I am trying to work with some of my students to possibly implement and experiment with a lot of those. And I gave a talk here once on the art gallery problem where I had a student that implemented 15 different heuristics for the art gallery problem. And some of them we got provable solutions because we had both upper and lower bounds and we could prove optimality. And there's been several efforts like that even though the problem is hard, hey, we can solve it to optimality, just like TSP. We can solve a lot of instances of optimality. For these problems, no one's done computational experiments to see what you can actually do with these typical methods for searching for optimal solutions.
Because then the third and final part of the question is that, so if you have these probabilistic methods, then sometimes you can actually get the result by showing that the probability of some event is non-zero, and that gives you existence. So
right, yeah, the probabilistic method.
Anybody looking at a probabilistic method for these problems?
In a sense, yes, because some of the methods that we have for approximating TSP, like the p-tasses, are based on randomization, and probabilistic arguments are used to prove the existence of certain structures. So that's, in fact, the basis of Aurora's polynomial-time approximation. I have a different method that doesn't use randomization, but probably works for the same reason that the randomization does. So his is probabilistic, mine's deterministic, but they're probably both getting at the same thing. Yeah.
But what is the nature of the O?
The nature of the O?
Is it like a number 10, or is it there exists a constant?
Here it's just that there exists a constant. I would claim that most of the big O's that I've thrown around today, the constants are manageable, double digits. I just came from my computational geometry lecture where we're starting to talk about Chazelle's linear time triangulation, a paper, the first paper in computational geometry Chris Bishop read was this notorious paper on linear time triangulation, and the big O there hides a factor that's bigger than a trillion. And we don't even know if that's an accurate, a conservative bound or not. So these are not ridiculous big O's. The big O's that I'm throwing around, I think I could actually compute double-digit constants with them.
Here for the higher dimension, I mean more than 3 dimension, it's just the general case. Do you have somewhere to use? I mean, except in math field.
Is there an application motivating it?
That's it.
It's a good question.
Yes, there is.
There is. Okay, well then Andrew will tell you what.
Yeah, we do a portfolio selection that you can. We're minimizing this smooth function, but it turns out there's lots of constraints, and so the constraints create a polyhedron, and it's fairly classical. Or we actually gave a talk in your CG seminar about 20 years ago, showing that that you can actually, when the art gallery theorems came out, we all got excited because there are these things called the Karish-Kuhn-Tucker conditions, the Kkt Conditions for Optimality, and if you can solve those, then you don't have to search for an optimum. You have an optimum.
Right.
And it turns out that the Kkt equations, for many of the problems that are interesting in finance, end up having a structure where the stationary paths are constructed in terms of being able to see various polygons or regions. So the art gallery problem, except we're anchored at 2 ends. We're going to get a path from A to B where it has to see all the stuff in between. So there are various fast methods, and at the moment they're not the fastest methods, so they're like in second place of what we're interested in. But they're faster than other classical convex optimization methods like interior point methods. Because what happens, and this is really why motivated my interest in the question about the offline, I mean the online version, in finance, the region that you're trying to get the visibility for is changing as you're solving it. This is an optimization, we call this the recourse problem.
Okay.
And so anything that would attack that would be wonderful. And also probably NP hard if it was really optimal. The dimension that we work in is anywhere from dozens to thousands. So there's your more than 3 motivation.
So maybe I should take further questions offline so that people feel free.
Okay, so let's
Thank you very much.